friends, welcome back to this online certification course on watershed hydrology. I am Rajendra Singh, professor in the Department of Agriculture and Food Engineering at Indian Institute of Technology, Kharagpur. We are in module 1. This is the last lecture, that is lecture 5 of this module, and the topic is rainfall frequency analysis. In this lecture, we will be talking about, we will be defining frequency analysis, and then we will talk about empirical methods of carrying out frequency analysis. Then we will see frequency factor method, and lastly, we will talk about intensity duration frequency curve. Now, coming to frequency analysis of rainfall, in fact, let me tell you that though we are talking about the frequency analysis of rainfall, but the principles remain true for any hydrological variable. So, it could be flood, it could be evapotranspiration or anything. The frequency analysis concepts remain the same. Only thing here we are talking in reference to rainfall. So, coming to a definition of rainfall frequency analysis, it deals with the chance of occurrence of an event equal to or greater than a specified magnitude. That is, if we have certain specified magnitude of an event in mind, then would like to know what will be its frequency of occurrence, and that is what this frequency analysis does. So, the objective of frequency analysis of hydrological data is to relate the magnitude of the extreme events to their frequency of occurrence through the use of probability distribution. So, basically as I said already that any variable that is a magnitude of extreme of that particular variable, we would like to link to the frequency of its occurrence, and typically we take the help of probability distribution. So, it is basically a statistical procedure, and data analyzed are assumed to be independent and identically distributed, and the system producing them is considered to be stochastic, space independent and time independent. That means, the data are considered to be independent, that means they are considered random. There is no correlation or there is no relation of a particular data in a sequence with the following data or the preceding data. So, they are all by chance, and that is how we say it is independent, and they follow certain distribution, identical distributor, that entire data in a series follows a particular distribution, and the system that produces that particular variable or data, that is considered to be stochastic, against chance. There is no trend, it is just a chance dependent, and it is space and time independent. Now, suppose P is the probability of occurrence of event x, which is rainfall, let us say, whose magnitude are equal to in excess of a specified magnitude, which is x t, which is generally referred to as P x greater than or equal to x t. This t will be suffix. So, it is basically P x greater than or equal to x t, where we are saying that a particular event x, and x t is a specified magnitude of that particular event or a specific magnitude. So, probability of x being greater than x t or exceeding this x t, if p, then the recurrence interval or the return period is related to p as t equals to 1 by p. That is, return period or recurrence interval is just the inverse of probability of exceedance in that particular case. The recurrence interval or return period, which is very significant, that represents the average interval between the successive occurrences of a rainfall of magnitude equal to or greater than x t. So, that simply means, if you have any particular event in mind, say x t equal to say 100 millimeters of rainfall in say 24 hours time. So, if this is the event we have in mind, then first thing is that what is the probability? Probability of x greater than 100 in 24 hours is probability, and t is 1 by p, that is recurrence interval, that is the average interval between the successive occurrence of rainfall of a magnitude equal to or greater than 100 millimeters in 24, if you know, that is nothing but the recurrence interval or return period. Just for example, if the return period of a rainfall event of 20 mm in 24 hours is 10 years at station A, then it implies that rainfall of magnitude equal to or greater than 20 mm in 24 hours occurs once in 10 years. That is, this, if the return period is 10, then it is we define there is a successive interval between successive occurrences, but that also says that it will occur once in 10 years. However, it does not mean that 10-year intervals will separate such rainfall event. That simply does not mean the periodicity. It does not mean that if the rainfall event occurred in 2010 and if it has a recurrence interval of 10 years or return period of 10 years, then it will occur in 2020 or 2030. That is not true. The periodicity is not guaranteed. Though return period is 10, the average interval between the successive occurrences is 10 years, which means if you consider a long period of time, say let us say if you consider a time period of 50 years, then we can expect that 5 such events in that 50 years period. So, if 50-year duration if you consider, then 20 millimeter rainfall in 24 hours may occur 5 times over that 50-year period, and thus there can be 2 or more such events within 1 year or month. So, I mean an event occurred in 2010 having a recurrence interval, it might occur again in 2012 itself. So, the periodicity is not guaranteed, but over a long period of time, yes, the average interval is 10 years. So, probability of accidents we have seen. So, probability of non-accidents of an event is P x less than x t is given by 1 minus P or 1 minus 1 by T, and it is generally designated by Q. And if we consider binomial distribution, then the probability of occurrence of a rainfall event r times in n successive years can be given by this formula, that is P r n, r times in n years is n C r. So, a combination is used n C r P r q n minus r. So, we know n C r is factorial n minus r factorial r, and P and Q we already know. P is the probability of accidents and Q is the probability of non-accidents, and n and r we have defined that n is the longer period of time and how many times that event occurs, that is, that it designates r. Also, the probability of non-occurrence of a rainfall event for n successive years can be found out, that is P x less than x t for n successive years, that is P 0 n, can also be found from this binomial distribution equation, and that comes out to be q to the power n or 1 minus p to the power n. Similarly, the probability of accidents of rainfall event at least once in n successive years can also be found out, and that comes out to be 1 minus q to the power n or 1 minus p to the power n. So, these 3 equations 3, 4 and 5 can be used to find out the probability of occurrences of event using binomial distribution. As I said, we have to have some distribution in mind. So, let us take an example, and the maximum one day rainfall depth of 20-year return period in a city is 150 mm. What is the probability of one day rainfall equal to or greater than 150 mm in the same city occurring twice in 20 successive years? And this question has been taken from GATE 2016. So, obviously, twice in 20 successive years. So, we can use binomial distribution for solving this problem. So, in that case, first thing is that we have to find out the probability of accidents, and we know it is the 20-year return period. So, probability is 1 by 20 or 0.05, and probability of non-accidents Q is 1 minus P or 0.95. So, we know P and Q. We also know that we have to find out 2 times in 20 years, that means R equal to 2, N equal to 20 in our case. So, we can use P, R N, N C R, same formula, and put the values in this equation, and we will get P 220 equal to 0.1887. Thus, the probability of one day rainfall equal to or greater than 150 mm occurring twice in 20 successive years in the city is 0.1887. So, that is the answer of this particular question. Now, let us take another example, example 2, that is one day rainfall of 200 millimeters at a place X was found to have a return period of 100 years. Calculate the probability that a one day rainfall magnitude equal to or greater than 200 millimeter will not occur at station X during the next 50 years and will occur once in next 30 years. So, again we have seen the formulation of these two cases using the binomial distribution. So, we can use that, and obviously first thing we have to calculate the probability of occurrence of the event P, which is 1 by T, and in this case the recurrence interval or return period is given in 100 years, that is T equal to 100. So, we can put that value. So, probability comes out to be 0.01, and probability of non-occurrence or non-exceedance P 1 minus P is, so P value already we have calculated. So, that will come out to be 0.99. Now, probability of non-occurrence of rainfall event for 50 successive years, that is P less than x t for 50 successive years is P 050, or in putting in this equation NCR P r Q n minus r. So, here we know that r equal to 0, n equal to 50. So, putting in binomial distribution, we get finally 0.99 to the power 50, which comes out to be 0.605. So, that probability that a one day rainfall of magnitude equal to or greater than 200 mm will not occur at station X during the next 50 years is 0.605. So, that is the answer of bit 1. Then similarly, we can solve for bit 2. Again the probability value that is remains the same, that is P equals to 1 by T, that is 0.01. Q 1 minus P also remains the same because we are talking about the same event. And what we have to find out, the probability of occurrence rainfall once in 30 years. That means our R value is 1 and remains 30. So, we can use the binomial distribution, and P 130 is NCR, that is 30 C 1, P to the power R Q to the power n minus R, that is 30 minus 1, and putting the values in this equation we get the value of P 130 is 0.224. So, that the probability that a one day rainfall magnitude equal to or greater than 200 mm will occur once in 30 years at station X is 0.224. So, that is the answer of second bit 2. Now, let us talk about frequency analysis of rainfall, and frequency analysis of a hydrologic events, say rainfall, may be carried out either by empirical method or by frequency method, frequency factor method. There are two possible ways of analyzing frequency analysis or carrying out frequency analysis. Now, first let us start with empirical method. Now, here the exceedance probability of the event is obtained by an empirical formula, which is generally called as plotting position formula. So, we use an empirical method of carrying out frequency analysis, we use plotting position formula. Now, there are several plotting position formula developed, and some of them are listed here in this table. Say for example, we talk about California method. So, in this method probability P is given by m by n. Here m is the rank assigned to the data after arranging them in descending order of the magnitude. So, any data series if you want to analyze, first thing you have to do is to arrange the data series in descending order of magnitude, and then you assign rank to every data. So, highest value will get m equal to 1, that is rank 1, and second highest will get m equal to 2, and so on, and last value will have a rank of m equal to n, that is number of data you have in the series. So, n is the number of records in the series. And so, we have California, Hazen, Weibull, Blom, Green-Gotten and several other formulae with different kinds of formulations, involving m and n. I mean, the variables remain m and n only, and out of these the Weibull formula is the most popular plotting position formula. So, Weibull formula which gives p equals to m by n plus 1, that is the most popular plotting position formula used especially for rainfall analysis. Now, what happens is that for the Weibull method, the probability is given by this. We have already seen from table p equals to m by n plus 1, and of course, the return period we already know t is the inverse of p or p is inverse of t. So, t comes out to be n plus 1 by m. Now, after calculating p and t, what we do is that having calculated p and t for all the events in the series, the rainfall magnitude is plotted against the corresponding t value, the return period, on a semi-log paper, semi-log graph paper, which is shown in the figure. So, on y axis we take rainfall magnitude in millimeters, and on x axis which is logarithmic. So, this is a log scale, as you can see also. So, this is a log scale, and the return period t is put on that, and then of course, you put all the values, and then typically this relationship is likely to follow a straight line curve. So, we have to put a straight line relationship. So, subsequently, the rainfall magnitude of any return period of probability can be determined by interpolating or extrapolating this plot. So, we have a plot. So, obviously, if you require rainfall for say 20 years, then you can straight away get from here, that is the magnitude. If you want say 50 years, then obviously you have to extrapolate. So, here 50 years will be here. So, you have to extrapolate. So, one drawback is that empirical method can give good results for small extrapolations, but the errors increase with the amount of extrapolation. So, as long as you are limited within the, or rather you are interpolating, your errors will be minimum, but the moment you extrapolate, and as much as you extrapolate, your errors will keep on going up. So, obviously, there is a caution that you avoid extrapolating, and even if you have to do, then do it to a minimal possible extent. Let us take example 3 here, and this example, that using the maximum daily rainfall data of expression x tabulated below, estimate the 24-hour maximum rainfall with return periods of 15 and 25 years. And second bit is, what would be the probability of rainfall of magnitude equal to or exceeding 100 millimeters occurring in 24 hours at this station, and the data is given here. So, we have 1967 to 1996 data, that means 30 years of data. So, n equals to 30 years in this, n is equal to 30, the 30 years data. So, n is equal to 30, and these are the data given to us. Now, first thing is, we saw that in using the plotting position formula, we have to arrange the data in descending order of magnitude and rank the data. So, this is what it is. So, obviously, first thing we have to do is, you have to scan through and find out where the highest rainfall is there. So, highest rainfall is this one. So, this value will be put first. So, here 137.7, which is the highest value, that will be put at the top, and we assigned a rank of m equal to 1. Then next highest value 131.9 will be assigned rank 2, and so on. And lastly, the lowest value, which is 40.1, that will be assigned rank 30, which is nothing but equal to where for this m equal to n basically. So, once we know m, we know n, then obviously we can use this Weibull's formula, p equals to m by n plus 1, and then we can calculate the probability, and t equals to 1 by p. So, we can calculate the return period. So, for all values we will calculate the return period and the magnitude, and once we have the values, then we will plot them. So, rainfall magnitude versus return period on a graph paper we can plot, and then obviously we can interpolate. So, what we have to do is that we have to find out the rainfall depth for 15 years return period. So, obviously, we know this is 15 year, we will draw a line, and wherever it cuts, we will find out the rainfall magnitude. So, it comes out to be 132 mm by interpolation. Similarly, if we have to find out 25 years of return period, so obviously we are still in interpolation only, because we have 30 years data. So, here against 25 years we draw a vertical line, and then horizontally we move and find out the rainfall magnitude, which comes out to be 152 mm. So, return periods by interpolation we have obtained. So, next, for the rainfall of magnitude equal to 100 years occurring in 24 hours, we have to find out return period. So, obviously, we will locate 100 mm here and then find out the corresponding return period, which comes out to be 5.5 years. Hence, the probability of rainfall of magnitude equal to or exceeding 100 years occurring in 24 hours is probability is 1 by T, that means 0.182. So, that means this is how we can use the plotting position formula and get the answers of whatever questions we have to once we have drawn the formula. Then comes the frequency factor method, and frequency factor method basically is based on the general equation of hydrological frequency analysis, which was given by Wen T Chow in 1951 and 54, and as per this formula, x t equals to x bar plus k sigma, where x t is value of the variate x with the return period t, x bar and sigma, that is these are mean and standard deviation of the variate, and k is a frequency factor which depends on the return period t and probability density function PDF of x. So, basically this equation what it says that we get x bar and sigma, that is mean and standard deviation, from the data series. Whatever data we have, we will get from the data series mean and standard deviation. Also, what we have to do is that we have to fit the probability distribution function to data to find out which probability distribution function our data is fitting into. And we know that from statistical knowledge, probably you know that there are various kinds of distribution functions available. And then of course, once we know the probability density function, and once we know for which return period or for what return period we are interested in getting the value of variate x, then using these two we can find out the frequency factor k, and once frequency factor is known, then because we know x bar and we know sigma, we can find out the value of x t using this general equation of hydrological frequency analysis. Now, for an assumed distribution, a relationship between k and t can be derived, and these derivations are already available. For normal distribution, which we use most frequently, this frequency factor k is equal to z, which is the standard normal variate. I think if you have used normal distribution anytime, you know what standard normal variate means. We will see that also in the next slide. Similarly, for log normal distribution, k can be found out using this relationship, where y is ln x. So, first thing what we have to do is we have to transform our data using logarithmic function. So, first thing what we do in log normal distribution means, first thing we do our data, we transform our data to log scale, and then we fit the distribution. So, so sigma y is basically nothing but the standard deviation. Mu y we have seen is the mean. So, mean and standard deviation here also is being used, and k y is y minus mu y by sigma y. So, y every single value is y once we have converted that, and then knowing mu y and sigma y, we can calculate k y and put here, and then calculate the value of k for using in the hydrological frequency analysis, general equation of hydrological frequency analysis. Now, just to give you an idea, I think you already know, but just to give you an idea, normal distribution or Gaussian distribution, which is basically a symmetrical bell shaped probability density function f x, and it is a 2 parameter model, mean and standard deviation, and it is given expressed mathematically by this relationship. And this is how we draw, I am sure that you have seen the graph of a normal distribution in statistics or mathematics, and you have also used that or fitted this. Now, this of course is the mean, the peak is the mean, and this is the standard deviation. So, this is this when we say this portion, this is mu minus the area between mu minus 1 standard and mu plus 1 standard, and this covers around 62% to 68.27% of the area. Similarly, if we consider this two that is within plus minus 2 standard deviation, then that covers 95.47 area, and lastly if you take these two extreme ends, then that is 3 standard deviation, which covers almost 99.73%. So, we have this kind of a distribution available. And in terms of standard normal variate, which is defined as z equals to x minus mu by sigma, then this distribution can also be written in this form. And standard normal variate has 0 mean and unit variance, and like for our normal distribution we have a normal table. So, for different probability distribution functions, there is normal, log normal, Pearson type, 3 extreme value, standard tables are also available for obtaining k. So, we have formulae also available and standard tables are available. So, you know, if you know T, you can read the value of k for using in the general equation of hydrological frequency equation. So, let us take in example, the following data present the peak discharge of river for 37 years. Compute the 100-year peak flow assuming that data follows normal distribution. So, already the distribution is identified to us and 37 years of data are given to us. So, 1967 to 2003 data are given to us, and we have been asked to compute 100-year peak flow. So, obviously, what we need to do is that, because we remember x t is x bar plus k sigma. So, first thing we have to do is, using the data series, we have to find out mean and standard deviation. The distribution function we typically fit, but already it says that it follows the normal distribution. That means, our k has to come from normal distribution or standard normal variate. So, from data we can find out x bar comes out to be 930.3, standard deviation comes out to be 290.4, and given t equals to 100, probability of accidents 1 by t 1 by t, that is 0.01, a probability of event less than 100 years is 0.99. So, obviously, what we do is that we take the standard normal cumulative normal table, which is available in any textbook, and we read the z value corresponding to 0.99. So, here 0.99 is there. So, we locate this point, and basically this table read like 2.33, this is 2.33, 2.31, 2.32, 2.33. So, z equals to 2.33 has a value of 0.9901. So, z equal to k is 2.33 for 0.99 value. Similarly, for any value we can read. So, say if it is 90%, let us say, so 0.90 nearest 0.90 is 9032, say for example. So, that means we can take the value of 1.3 h k. So, once we know the k, then we know mean x bar, we know standard deviation, we know k, then k x t can be calculated as 1607.04 cubic meter. Thus, the 100-year peak discharge for the river is 1600.04 cubic meter per second. Similarly, we can fit a Gumbel extreme distribution also. For Gumbel extreme distribution, k t is calculated by this formula, and it is a function of t only, that is recurrence interval. So, it is very simple. So, another example, for the data compute 20-year flood assuming data follows the Gumbel distribution. So, obviously, here again the data are given, and we already have calculated mean and standard deviation. So, what we have to do is that for 20 t equals 20, we have to calculate the value of k t. By putting in this equation, we get k 20 or k value is 1.866, and then we can use the general hydrologic frequency equation to get x 20 using the Gumbel extreme value type distribution, and that comes out to be 1472.28 cubic meter. Thus, the 20-year flood magnitude is 1472.28 cubic meter per second. So, that is how we can use the frequency factor method for finding out or fitting the or for carrying out the frequency analysis. Now, let us discuss the intensity, duration, frequency curve once we have talked about frequency. So, intensity to frequency curve is most commonly used tool for relating storm frequency to the magnitude, and it is a intensity versus duration graph having a series of curves, one each for different return periods. So, here you can see that we have intensity here, duration here, and these are curves for different recurrence interval of frequency or recurrence interval. So, once we from using this curve, we can for any recurrence interval and any duration, we can find out the intensity of rainfall, and it is typically derived using precipitation data of many storms, and it depicts the intense burst of precipitation. The precipitation intensities for different duration frequencies are needed for designing runoff disposal or erosion control structures. So, anytime we design a runoff disposal or erosion control structure, we have to find out what is the 10-year max rainfall intensity or magnitude. So, using this intensity duration frequency curve for different durations, we can find out what is the intensity of the curve. And typically we use average intensity, that is I equals to P by T, where P is the rainfall depth and I is the rainfall duration. And frequency, of course, we have seen that it is in terms of return period, we express that, and minimum of 20 years rainfall data is desired for intensity duration frequency analysis. So, besides frequency analysis, frequency rainfall intensity duration frequency curve, people have also tried to derive general relationships of IDP, and one such equation is given here, which was derived by Kothari and Garde in 1992, who analyzed data from 80 rain gauge stations across India and developed this relationship. So, here ITT, that is rainfall intensity in millimeter per hour for T year return period and T hour duration, can be found out by T and T, of course, we have defined. R 224 is rainfall of 2 hour return period and 24-hour duration in millimeter. So, for that location you have to have R 224 data, and C is a constant, and Kothari and Garde, they also recommended values of C for different zones in the country. So, for northern zone the value of C is 8, for central zone it is 7.7, for southern India it is 7.1. So, using this C value and T and also knowing R 224, that is rainfall of 2 year return period and 24-hour duration, we can find out rainfall intensity for desired duration and recurrence interval. And this equation I have taken from Kothari and Garde, a paper published in Journal of Hydraulic Engineering ASC at 118 2 in 1992. So, with this we come to end of this rainfall frequency analysis. Thank you very much for your patience hearing, and please feel free to give your feedback and also raise your doubts or questions in your forum, which can be answered. Thank you very much.